Okay, I wanted to make this little video about complex conjugates because they're very useful when you're talking about complex eigenvalues and eigenvectors. And if you know a little bit about the properties of complex conjugates, many proofs can be very simplified. All right, so what's the definition of a complex conjugate? Complex conjugate of the complex number a plus bi, that's a complex number, is a minus bi. Okay. Sometimes we write the complex number as a single letter, like z. So if z is a complex number, then the complex conjugate of z is written as either z star or z bar. Now, typically when I have vectors, I'm going to write star for the vectors. What's the complex conjugate of a vector? Well, you take the complex conjugate of each component. But if I'm not talking about vectors and I'm just talking about numbers, typically I'll use z bar. But you should be aware either z star or z bar can be used for complex conjugate. All right, so here's some facts about complex conjugates. Very simplifying facts that make algebra with complex conjugates a lot easier. So let z and w be any arbitrary complex numbers. First fact is that the complex conjugate of the sum of two numbers is the sum of the complex conjugates. And you can write that, you can simply write that proof down if you write z as a plus bi and w as c plus di. And you do the algebra, you'll find this is true. Second one is the complex conjugate of the product of two complex numbers is the product of the complex conjugates. Third is that the complex conjugate of the reciprocal of a complex number is the reciprocal of the complex conjugate. So what this allows you to do is when you take complex conjugates of algebraic expressions, you can simplify quite a bit. Let me give an example up top. Let me, for instance, let me prove this z bar, w bar. Okay. I'll prove this second identity here, that z bar w bar is the complex conjugate of zw. Well, I can write this as a plus bi times c plus di. And I'm taking the complex conjugate of each one. So that's the same thing as a minus bi, that's the complex conjugate of a plus bi, times c minus di, that's the complex conjugate of c plus di. And I can do the, multiply this out using Floy. First is a times c. Last is bi times di. The i's give me an overall factor of -1. I also have a -1 on the b and a -1 on the b. Altogether, 3 minuses gives me a minus. So that's ac minus bd plus, the other two factors are going to be imaginary. If I take a times minus di, that's going to be minus a di. I'm going to factor out the I because the other term also has an I. So I've done first, last, outside. Now I need to do inside. And here I'm going to have a minus bc. So I do a little magic with minus signs. That's ac minus bd minus ad plus bc times I. And you can verify that that's the same thing as a plus bi times c plus di complex conjugated. Okay. Now, an application of this would be something like this. Suppose I have a complex number and I raise it to the nth power and I want the complex conjugate. Right? That's the same thing as z times z times z, blah, 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 times z. And you're putting a big bar over everything. Now, what this fact says is that if I have a big bar over everything, so let me finish this up, that's the same as zw bar. If I have a bar over the product, I can split it up into bars over the individual factors. So that's equal to z bar times blah, blah, blah times z bar. I mean, that's the whole point of this proof here, is that if I have a bar over a product, as I just said, I can split that up into bars over the individual factors. I can just apply that repeatedly here. So I started out with a bar over z to the n. I have the bar over all n factors. I put the bar over each individual factor. What I get here is z bar to the nth power. Okay, very useful. All right, let's see what else we have here. So I've been through these three. I've explained, I've talked about this. This one also you can write down and show explicitly by writing z equals a plus bi. It also turns out if you have a complex number and you add its complex conjugate and divide by 2, then you get the real part of that complex number. So what are we talking about here? If you take a plus bi plus a minus bi and divide by 2, work it out, you'll just get a. Okay? So you should be thinking of z as a plus bi having a real part and an imaginary part. Similarly, you do the same sort of algebra, and if you take z minus its complex conjugate, divide by 2, you get its imaginary part. So if I did this with a plus bi, I would get b. Two more important facts here. If a is real, then a is equal to its complex conjugate. All right, because you know the complex conjugate is going to be a minus bi, but b is 0, so you just have a. On the other hand, if ai is imaginary, then the complex conjugate of ai is equal to minus ai. Okay, so the complex conjugate of a pure imaginary number is the negative of that number. If I have complex polar form, I need to move this up here. If I have complex polar form, you can write a complex number as r times parenthesis cos theta plus I sine theta, where theta is the complex angle. You plot it in polar coordinates here, right? You've got the angle here. This is theta, this is r, and here's the complex number z. Okay. So if I take the complex conjugate of this, well, I can use the rule that the complex conjugate of a sum and product is equal to the sums and products of the complex conjugates. You can work this out, that the complex conjugate of r is r, complex conjugate of cosine theta is cosine theta because it's a real number. Complex conjugate of I sine theta is minus I sine theta. And if you remember your trigonometry, cosine of theta is the same as cosine of minus theta because cosine is an even function. And sine of theta is equal to minus sine of minus theta because sine is an odd function. So I can replace this minus sine theta with sine of minus theta. Right? And that can be seen geometrically. If I have z up here, the complex conjugate of z will be down here. This angle here is minus theta, and here I have z bar. Okay, so we see both from geometry and from algebra that the complex polar form simply reverses the sign of the angle. Okay, now we can use these facts to prove many things about solutions of equations. Okay, first proposition, if z is the root of a polynomial with real coefficients, then so is its complex conjugate. All right, the proof is just algebra. Let's write the polynomial as a n z to the n plus a sub n minus 1 z to the n minus 1 plus dot 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 down to a sub 1 z to the 1 plus a sub 0 z to the 0. So I use indices to indicate the coefficients of the polynomial. And here the ai's are real. Now, if z is a root of this polynomial, then we can write down this equation. Write the polynomial again with z there. That should be equal to 0. That's what root means. Now I have an equation. I can always do the same thing to both sides of an equation. So I'm going to take the complex conjugate of both sides. And I'll use the rules above to simplify. So for instance, what is the complex conjugate of an times z to the n? Well, the complex conjugate of an is an, because an is real. The complex conjugate of z to the n is the z bar to the nth power. That's what I just showed up here. Right? That's what I showed up here. The complex conjugate of zn is equal to the z bar to the nth power. Okay. Oops, sorry. Let's get back there. Where are we? All right, so we started with this equation that expressed the fact that z is the root of this polynomial. And taking the complex conjugate, we end up with this equation. What does this tell us? This tells me that zn bar is also a root of the very same polynomial. So z bar is also a root of the same polynomial. So this expresses the fact that the roots of polynomials come in complex conjugate pairs. Polynomials have real roots and complex roots. The real roots are not paired, but anytime you have a complex root of a polynomial, there's another complex root, which is this complex conjugate. Okay, so let's use this to prove some facts about eigenvalues. Proposition: if lambda is an eigenvalue of our real matrix A, real matrix means all the entries in A are real, then the complex conjugate of lambda is also an eigenvalue of the same matrix. Okay, the proof? It's pretty much the same proof that we just did for the previous proposition. Lambda is an eigenvalue of the real matrix A. What does that mean? That means that the determinant of A minus lambda I is equal to 0. That's the defining condition for an eigenvalue. What that tells you, if you're a linear algebra fan, it tells you that the rank of this square matrix is less than the size of the matrix. And it means that there's you can find a homogeneous solution to A minus lambda I times V is equal to 0. Right now, what about this expression, determinant of A minus lambda I? This determinant is actually a polynomial in lambda. If you're not convinced of that, you can go to Wolfram Alpha and type in any matrix and find the determinant, and you'll find that, in fact, it's a polynomial. It's called the characteristic polynomial of the matrix A. Okay? So this equation, determinant A minus lambda I equals 0, is a polynomial equation. And lambda is the root of the characteristic polynomial. Now, if A is real, this polynomial also has real coefficients, because the coefficients are algebraic expressions based on the entries of A. So we have that the lambda, being an eigenvalue, means that lambda is the root of a polynomial with real coefficients. Okay? From this previous proposition, lambda bar is a root of the same polynomial. Okay, what does that mean? That means that, I can just say that, so that means that the determinant of A minus lambda bar I is also equal to 0, because it's the root of the very same polynomial. So lambda bar is also an eigenvalue of A. Finished. Okay. Now, last proposition. If the vector V is an eigenvector of the real matrix A, then so is its complex conjugate. Again, the complex conjugate of a vector, you simply take the complex conjugate of all the entries in the vector. Okay? So here we're saying if V is an eigenvector of A, then so is V star. So for the proof, let's start with the presumption that V is an eigenvector of A. What does that mean? The defining condition for eigenvector is that AV equals lambda V, where lambda is an eigenvalue of A. Take the complex conjugate of this equation. Now, what's the complex conjugate of the matrix A? Well, it's the matrix A because the entries are all real. What's the complex conjugate of the vector v? Well, the complex conjugate of v is v star, where I take the complex conjugate of all the entries of v. What's the complex conjugate of lambda? Well, that's lambda bar. And here I have v star again. So what do I have here? Here I have the defining condition for the eigenvector corresponding to eigenvalue lambda bar. So v star is an eigenvector of A corresponding to the eigenvalue lambda bar. Finished. I've shown that if v is an eigenvector, then so is v star. Okay, so hope that helps a little bit with some of these complex proofs involving eigenvectors and eigenvalues.